Beats. Here we have a wave of a certain frequency and a certain amplitude. If we add to it a second wave of a similar frequency and a similar amplitude, we find that at this point and at this point the two waves are in phase and will constructively interfere, producing a wave of roughly twice the amplitude. At this point the two waves are out of phase and will destructively interfere or cancel each other out. What I have here is a sum of the two waves above, and we find at this point where the waves were in phase we end up with a wave of twice the amplitude and the average frequency of the two waves above. We get the same thing here with twice the amplitude and the average frequency of the two waves above. In the center, however, the waves cancel out and we get effectively zero amplitude. If we outline the waves, we end up with this type of situation where we have a large amplitude, effectively a zero amplitude, going on to a large amplitude again. This gives us our beats. Beats can occur with any type of wave, but I'm just going to demonstrate their effect now on sound waves. I have two signal generators connected to speakers, both emitting a similar frequency and similar amplitude sound wave. What you should hear is the volume of the sound rising and falling. This is the beats. Beat frequency. In time t, a note will complete ft cycles, as f is the frequency or number of cycles per second and t is the number of seconds. If we have two notes and in time t, note 1 completes one more cycle than note 2, f1t, the number of cycles completed by note 1, minus f2t, the number of cycles completed by note 2, will equal 1. We can rearrange this to give t is equal to 1 divided by f1 minus f2. This is the beat period, the time between one beat and the next beat. But frequency is equal to 1 divided by time period, and so we can say that the beat frequency is equal to frequency 1 minus frequency 2. I will now demonstrate this with the two signal generators connected to speakers that I used before. This time the first sound will start with a lower frequency than the second sound, but I will slowly increase its frequency so it passes through that of the second sound and rises above it. What you should hear is the beats starting with a rapid frequency, the frequency reducing effectively to 0, and then increasing again as the difference between the frequencies gets smaller and then larger again. We can use this effect when tuning musical instruments. We play a note and also play a tuning fork of the same note. We adjust the note on the instrument until no beats can be heard. Now the frequency of the note is the same as that of the tuning fork. The human ear can detect beats of up to around 7 Hz and down to around 0.1 Hz. This allows us to get the note of the instrument very close to matching the note of the tuning fork. Beats and quality. The same note will sound different on different instruments. The note is made up of the fundamental frequency, which will be the same for both instruments, but also contains overtones. The fundamental frequency will usually be the strongest, and the relative strength of the overtones gives the quality of the sound. The strength of the overtones will vary between instruments and is what makes the same note sound different when played on a piano compared to a violin, for instance. These overtones can produce beats, which will also contribute to the quality of the sound. I'm now going to play the same note on a violin, then a trumpet, then a clarinet. You should clearly be able to tell that they are three different instruments. You should also be able to tell that they are playing the same note. You should notice also that these instruments do produce beats of differing frequencies. That showed you the different quality or different sound of a violin, then a trumpet, then a clarinet.